All right, so in our lab, we climbed some stairs, right? So here we are, down here, at the bottom of our stairs. And we climb our stairs, not very even, to a certain height, right? So there's some height of stairs that we have here. And I think our stairs were somewhere around 180 centimeters if we measure them. So somewhere around there. It might be a little bit different. But as we come up here, we're changing our height. So since we're changing our height, what we're doing is we are adding energy to our system. If we say that we are our system, right, down here we can say that we really have no energy. But as we climb our stairs, then we gain gravitational potential energy because we've gone up to some height. We've changed our height above our reference point. Now we know that our gravitational potential energy is equal to mgh. So whatever our mass is, we can find our gravitational potential energy because we know how high our stairs are. So let's just make this up. Let's just say that, I don't know, Susie over here has a mass of 50 kilograms. All right, so her gravitational potential energy is going to be 50 kilograms times g, which is 10 newtons per kilogram, times a height in meters. So we want to convert this to meters. So we're going to divide by 100. So 1.8 meters. So if we take 50 kilograms times 1.8 meters times 10 newtons per meter, we are going to get, that doesn't look right. Let me recalculate that. So if we take 50 kilograms times 10 newtons per meter times 1.8 meters, we're going to get 900 joules of energy. Okay, so Susie, when she went from here to here, she gained 900 joules of energy. Now, if we take Timmy, let's just say he has a mass of 75 kilograms. We'll do the same thing. So we'll take our mass times our 10 times our 1.8. So he went the same height, but he has more mass. So he gained 1,350 joules of energy. Okay, so they both started down here and ended up here. So the amount of energy that they gained was different because of their mass. So Susie gained 900 joules and Timmy gained 1,350 joules. Now this is also the amount of work that was done, right? So in order to go from here to here, we had to do work, right? This is our change in energy is our work. So since we changed energy, we did work. Now the other part of our lab was to see how long it took us to go up the stairs. All right, so we walked up the stairs and then we ran up the stairs. So when we determined the amount of work done by running up the stairs and the amount of work done when we walked up the stairs, what we notice is this is the same thing, right? The amount of work is the same. It doesn't matter if you do it quickly or slowly. The amount of work that you do when you go from the bottom of the stairs to the top is going to be the same. All right, so let's just say that Susie when she walked, she took 6.3 seconds. So she walked up the stairs in 6.3 seconds. She ran up the stairs in 2.3 seconds. Okay. Now what we can do with that is we can find out the rate of work that's done. Okay. So this is called power. So when we talk about power, whoops, I missed the line there. This is the rate of work done. Okay, now anytime that we have a rate, we're talking about the amount of time that it takes us to do that. So power is actually work divided by time. So for Susie, the power that she exerted when she walked up the stairs is going to be 900 joules, because she did 900 joules of work, and it took her 6.3 seconds to do that. So her rate of work was 143 joules per second. Okay. Now we have a special name for that joules per second. Okay, so when we talk about work, we have joules per second. This is called a watt, and it's abbreviated with the W. Now what I want to point out, this W here is not the same as this W here. This W is work. This W is watts. So if it's a variable, it's work. If it's a label, it's watts. Now if we take her other time, it still was 900 joules of work done to go from the top to the bottom. But when she ran up the stairs, it only took her 2.3 seconds. So the power that she exerted was 391 watts. Okay, so this is watts as well. So the amount of energy that it took for her to go from the bottom of the stairs to the top of the stairs is the same, but when she ran up the stairs, it took her less time, so she exerted more power. Okay, so we can do the same thing for Timmy, and let's kind of compare that. So Timmy took 1,350 joules, and I don't know, let's just say it took him 8.3 seconds. He's a little bit slower. So he did 1,350 joules of work, and it took him 8.3 seconds. His power is going to be 163 watts. All right, so even though he was slower, he exerted more power, mostly because he's bigger, right? Because of his mass. So it took him more energy to go to the top than it did Susie, and so he exerted more power. Now let's just say he goes 1,350 joules, and when he runs up the stairs, he does it in 4.12 seconds. I'm making those numbers up. So 1,350 divided by 4.12 is going to give us 328 watts. So this is kind of interesting. So even though he's bigger and he needed more energy, it took him more work to get to the top of these stairs, he was slower, right, than Susie. And so he required less power when he ran up the stairs. So it's kind of interesting. So you can be smaller and have more power if you're faster. What if George comes along here and takes the elevator to the top of the stairs? Let's just say that he has the same mass as Susie. He has a mass of 50 kilograms. Okay. What is his amount of work done? He looks kind of weird there. All right. What is the amount of work that he has to do in the elevator, or the elevator has to do on him, to get him to the top of the stairs? Now, the work here is still that gravitational potential energy, right? So the amount of energy that it takes to get up here is the amount of work that the elevator has to do to take, what's his name, George, up to the top. So it's still mgh. So if we take the same mass as Susie, and then 10 newtons per kilogram, times 1.8 meters, so he's going the same height. Okay, if you calculate that, the amount of work that the elevator has to do on George is going to be 900 joules. So it doesn't matter if you walk up the stairs, or if you run up the stairs, or if you take the elevator. The amount of work that is done by you or on you to get you from here to there is the same. Now, our elevator is pretty slow. I really don't know how much time it takes to go from the bottom to the top. Let's just say that it's, I don't know, is it going to be faster or slower? Honestly, when somebody is getting into the elevator at the bottom of the stairs, I typically beat them. So let's just say that it takes 15 seconds. Is that a good time? So there's 15 seconds that it takes for our elevator to go from here to the top. So the amount of power required by the elevator. I forgot what I was doing there. Okay, so that's still going to be work divided by time. The amount of work is going to be 900 joules, but it's going to take 15 seconds for that to happen. So if we take our 900 and we divide by 15, we are going to have 60 watts of power. So it doesn't matter. So when we talk about how you get to the top, it doesn't matter. Okay, you can walk, you can run, you can take the elevator. Your work is all going to be the same. But your power changes depending on how much time it takes you.